Okay, so we are in lesson 3 of module 3, and we're going to start to talk about normal distributions. So as I alluded to yesterday, normal distributions are density curves that are symmetric. So that's the first thing I want to talk about and get that out of the way because that's really the main point of a normal distribution. A normal distribution is going to have this really nice symmetric bell-shaped uh, curve appeal, and that's going to mean that the data was a histogram, for example, a histogram that was symmetric. Then we're going to draw this curve around it, so it's a density curve. We're going to color it in, and we're going to say, you know what, our data can now follow this normal distribution, which is going to allow us to use z-scores. So normal curves, the only reason that we've created that nice normal curve around our data is to actually take a z-score and apply that, which is really important. So since all testing, like standardized testing, follows this really beautiful symmetric curve, that is why we can standardize the test by drawing that line over it, establishing a mean, establishing a standard deviation, and building this normal distribution that we can calculate z-scores from. So that's really the big idea of today and a normal distribution. So I go through and kind of explain that within the notes if you want to look at it. It's symmetric data, it's single peaked, it's bell shaped. We're going to use mean and standard deviation because it's the same as the median. Your center is going to be the same as the median. So we're going to use mean for this one. And then we start talking about how we build these normal distributions. So normal distributions look like this. They are a bell shape like this. The mean is right in the middle. We have two different ways that we're going to show mean. X bar is what we've been using because we've had data. This mu right here, that's what that symbol is. It's a mu. It kind of looks like a U or like a M of some sort. But that mu is going to mean that it's a population standard deviation. I'm sorry, a population mean. We'll get into that more later on. Just like our standard deviation symbol, you're going to see this as a standard deviation symbol, and that means it's a population standard deviation. What I've been using is S of X bar, and so just note that this is a different way to say those very same things for us right now. So you'll notice that there are 3 standard deviations in either direction. If you watch the other lessons, I already kind of alluded to that being the case. Anything that's bigger than 3 standard deviations is going to be super, super rare, and we're going to call it an outliner or an outlier within our data. Actually, really anything that's more than 2 is kind of outlier-ish or rare, what we call rare in real life data. So a normal distribution, we talk about these points of inflection. They kind of talk about the inflection points as where the standard deviation points are. But basically, if you guys are thinking about how to draw this normal distribution, you want to make sure your standard deviations are about equal distance away from each other and that you can fit 3 on one side and 3 on the other. It talks about in the book how like you run down here, and as you start to get steeper, then you put 1 standard deviation and then it flattens out, so there's your second one. But in reality, what you really are looking for is the spacing here. You want to try to make them equal spaces, and you want to try to fit 3 standard deviations out on the tail. So we get into what's called the 68, 95, 99.7 rule. And you will have a couple problems pertaining to this, so really understanding this is important. In a normal distribution, if the data is symmetric, then it should follow suit with this right here. 68% of the data should be within 1 standard deviation. 95% of your data should be within 2 standard deviations, and that would mean we only have 5% on the outside, like 5% in either direction on the outside, which would mean that 99.7% of our data needs to be within 3 standard deviations. If this rule does not happen, then it means that your data is not symmetric. You are trying to take something and fit it to a normal distribution, and it's not normal data. So that's really the what the 68, 95, 99.7 rule means. It means that if it doesn't follow that, if 68% of your data is not within one standard deviation in either direction, that's positive and negative, then that means that your data is not symmetric. So you cannot use z-scores. But symmetric data will follow this right here, that 68, 95, 99.7 rule. And I'll show you an example of what that looks like in your homework problems. So go down to there if you want to see more about that rule. Okay, so what we're doing today primarily is calculating z-scores. Once you have this normal distribution, and I have, like here, I have that the normal distribution has a mean of 0, and it shows me 1, 2, and 3 standard deviations in either direction. So this is where we have a -1, -2, -3, meaning it's a -1 standard deviation away, a -2 standard deviations away. If your score on a test was down here, it means you scored below the mean, because this would be the mean here. So we're going to talk more about that. This right here is where we finally get introduced to the chart, and I'm going to show you an example. So you'll pop over in the example portion of this, where we finally get to use our z-score chart for figuring out what percentile something is in. So we're going to be looking up z-scores. So in this example right here, if I have a z-score that is less than -2.25, we're going to be drawing a curve. That will be our very first step, is to draw this curve. I'm going to locate, so -1 standard deviation away, 2 and 3, -2.25 would be way down here. And then I'm going to color in because I want less than. I'm going to color that in. We're then going to go to the table, and I'm going to show you this again in the example so that you can see a better fit. There's a negative side and there's a positive side to this z-score sheet. This was a -2.25, so I go to the negative side and I look up that z-score to figure out what the area is. You'll see here that I have an area when I look it up of 0.0122. That's the area to the left. I want to make it clear that in this Z table, and again, my example will show this better. I'm going to pop over and do this entire example that I'm kind of showing you now. I will be showing you on the next slide, but the area is always to the left. It's always to the left. They actually show the shading here. That's always to the left, and I'm going to establish that in the example video, but that is what you're looking up. So there are a couple processes that we're going to have to go through. Like when they ask for the area to the right, I will have to do 1 minus the area to the left because I want the other. But I'm using that principle of the area under my curve is always 1. So if this is 1 and I got that the area to my left is 0.012, well, the area to the right would be 1 minus that. So we're going to establish this in the example in the next video. Before I leave this to do this example right here, I am going to tell you that our process for these problems will be to first always draw a picture and shade it in the right direction. Then we're going to standardize the score. So then we're going to find the z-score. So I drew a picture. I put where, like, and I did my shading. I put what part I want. Then I calculated a z-score, which in this problem, it's actually already given to me. But in the problems that we have for homework, we're going to calculate a z-score. So I standardize it, meaning calculate a z-score. And then I go to this table to look up the percentile here. We are using the idea that the area under the curve equals 1. That's from density curves yesterday. So that ties into what we're doing today. And then we rewrite the problem. So pop over to the next video so that way you guys can see the example, because that's probably the most important part of this video.